I will be talking about bootstrapping the Yang theory together with my PhD advisor, Volodya Kazakov. And this kind of bootstrap, nowadays it is usually called the lattice or matrix bootstrap. That there is several closely related projects here. So initially, it began with Anderson and Kuczynski already 7 years ago about the Yang theory, and here in time and our previous result, they are on the matrix model or matrix quantum mechanics. And this one is the afterward is using the similar method on the easy model. So and this general framework, it is also applied to the so-called quantum mechanics bootstrap, or someone also call it the many-body bootstrap. So this same framework optimization can use to get some result on the numerical result on the quantum system, and also even the classical dynamical system. Or even the turbulent system. So, in my point of view, this kind of methodology, it shows an endeavor to reformulate the physics problem into the framework of the optimization theory. So it is a bit similar to the language of the quantum information, where some physical quantities, it is defined by the optimal solution of optimization problem. So because the background of the audience here, majority they are condensed matter based. So I will begin with the simplest toy model. So it is, I would like to call it the zero-dimensional phi-4 model.
It was supposed to be 50-50. That's spontaneous symmetry. Right?
Okay. But the top is already not 50-50. So this is the model.
Would you mind making it a little bit bigger? Sorry,
oh,
I know
sorry.
I'm sitting maximally far.
Or a lot bigger.
Sorry. Where is the eraser?
It's at the top, above the formula. Yeah.
Oh.
Alexei, are you getting old?
Definitely getting
Yeah, this is maybe the simplest non-trivial integration. Otherwise, if G is 0, then it is a Gaussian integral. So by the bootstrap method, solve it. Well, the first observation is a Schwinger-Dyson equation. That is, you do under this integration, you do a change of x to the x plus epsilon. So this doesn't shift anything. This is the definition of the integration. What you will get? Well, equivalent, you will get the following equation. This must be 0, right? So what do we want to solve? Our goal is to solve the case moment of this under this partition function. So this will tell us that yeah, this is a recursion relation, and also the Schwinger-Dyson of this simplest model. And also we have the word identity. What is it? Well, we give a redefinition that x to the minus of x. What do we get? We get wk plus 1 equals minus wk plus 1 when k is even. Also here, we do this shift here. And this means that wk equals 0 ko. And the third one is positivity. polynomial is square, the expectation is positive. This is obvious. Why? Because this is a positive function integrated over a positive measure. So the result is positive. What does this mean? Well, this means that the coefficient, the coordinate vector of the coefficient, it must be, this inequality must be true for any Rn vectors. So you can write it into a quadratic form. Because it's bilinear. And what is the matrix in the middle? Matrix in the middle, Mij equals Si plus J. How it looks like? It looks like M equals W0, W1, W1. Here, here is the definition of Wk. W2, W4, W3. Sorry, I made a mistake. This is an infinite dimensional matrix in principle.
So you're using W to 0.
Yes, so there is a lot of zero in this matrix. And also, by looking at the recursion relation, I remind you that W0 equals 1 by normalization. So, and all the numbers, they are all 0. The even numbers, you can solve this recursion relation, what you will get. Well, you can solve the W4 in terms of W2, because W0 is 1. So what's the final result? The final result is Wk. You can always express it by some linear term, constant term plus some linear term. They are all the linear functions of W2. So this matrix, although it looks complicated, is a algebraic inequality for the W2 for any given G. For example, you put G equals 1. So we can put some truncations of this big matrix, infinite dimensional matrix, and we use optimization theory. What would we do? No, I shouldn't do that. Is this right?
Yeah.
Okay. We want to minimize or maximize W2 under the constraint of the positivity of this matrix. So let me put it here, M lambda plus 1, positive semi-definite. M lambda plus 1 is, I take the truncation and top lambda plus 1 times lambda plus 1 submatrix. It is positive semi-definite. So how does this work? Well, this must be true, but it is not apparent for us that it will give us useful information. But let's have a look. So G equals 1 and lambda equals 10. What is the result?
Where does this constraint come from?
Sorry?
What is that M lambda plus 1?
Yeah, this is the top lambda times 1, lambda, okay. This is the top lambda plus 1 times lambda plus 1 submatrix of this infinite matrix. So this is a Hancock style matrix, right? It can be infinitely.
I understand.
Okay.
I thought you were writing indices.
No. This is the indication of the truncation or the bootstrap order. So you get 7-digit precision of the result. What is the exact value of W2? Well, you have the, because this simplicity, you have the closed form expression in terms of some Bessel functions. So you can evaluate it as much as you want. Maybe some idea.
So in terms of numerical resources, how does it compare to Hamiltonian truncation?
There is this is zero-dimensional system, so there is, I don't think there is a Hamiltonian truncation, right?
Yes, I mean that's probably how you got the exact number.
random number, I just got it from the closed form. You have the closed form in terms of the modified Bessel function.
Oh, it's zero. Sorry, it's zero.
Okay.
Question?
Yeah.
In this method, is it important that G is positive?
G is positive. Well, yeah. If you take G is negative, you will get the max. If you want to take the minimum of, you cannot find any valid solution for W2. So you solve this inequality, you have no solution. If G is smaller than 0. If G is 0, what will happen? It is when G is 0, then this you can solve every moment just by the Schwinger-Dyson equation. You don't need the positivity. Okay.
Is there a quick way to see why you get a two-sided graph?
Sorry?
Is there a quick way to see why you get a two-sided graph?
Oh, so you mean why this works?
Yeah, so when
Two-sided bound.
two-sided.
So I take the maximization or minimization of W2.
Yeah, but the condition you have is only.
Well, the condition here is an algebraic equation. That is, this matrix is positive semi-definite. What does this mean? This means that all the principal minor of this matrix is positive. What is the principal minor? That is pole. The submatrix is determinant. They are all positive. This is an algebraic inequality, so it will have a lower bound and upper bound. Yeah.
Does the technique fail if there's a sign problem? If you add to your action, I don't know, ix cubed?
Yeah, when there is a sign problem, it's non-trivial to make it work. Sometimes it is.
Because
it depends on some PT symmetry. You must be aware of it. Sometimes it can work.
is it the positivity that fails?
Yes.
That's what I was my guess.
Yeah. There might be some sign issue, but sometimes you can get over it. But sometimes we don't have a clear solution at the moment.
In physical systems, we certainly have PTs.
Well, for phi cube you have it, but for the others, well, if you have the PT symmetry, then you have real eigenvalues for the Hamiltonian. So
Right,
this is
those are physical systems, at least in your physics space, right?
Yeah, in some sense.
So maybe there's a way to impose for physical systems with the sign problem.
Might be. Yeah, but this is an open problem because for some
I
problems.
guess refraction positivity would be the thing that you impose.
Yes, but I will talk later that for a given system there might be different kind of positivity. Sometimes just by reflection positivity you can get no bound. There is no bound you can get. Yeah. So this is not guaranteed to work. The result must be correct. It is rigorous. It's almost rigorous bound. But you are not guaranteed to get a valid bound. This is the problem. There are some theorems to guarantee it. So I would like to remark on why this works, or is there any heuristic argument that tells us this works? Well, the most easiest way is that when you are trying to do a numerical evaluation, say in Mathematica, what you should tell Mathematica. The first thing you should tell is that what your function is. But this is not the end of the story. You need also to tell Mathematica what is the measure space. Where are you doing the integration? For example, you are from the minus infinity to the infinity, or from 0 to infinity. This is what you need to tell Mathematica. So here is the same idea. So the Schwinger-Dyson equation here basically tells what is the measure, or what is the potential you are taking the integration. And the positivity condition here, what it tells that you are doing the integration on a positive measure on the real axis. So this is guaranteed by the result of the mathematical theorem that's called the Hankel moment problem. That is, positivity of the moment in terms of Hankel matrix is equivalent to positivity in your measure is defined when you have a positive measure on the real axis. This is an equivalent condition. Okay, so this finished our discussion of this simplest model. And I would like to remark a bit on quantum mechanics bootstrap. Why this framework can be generalized to the quantum system. Let's also think about the simplest system that is, for example, the 1 plus 1, 0 plus 1 dimensional quantum system. So what should be the measure here? Or what should be the partition function here?
Quick question. Does this get bad at large G?
Large G. Yeah. It is purely. I didn't. Sorry, I can show you later the plot when you are varying G. So this is intrinsically non-perturbative. So it works both for small G and large G. It doesn't matter. You will get exponential convergence. Yeah. So quantum mechanics. Now, d mu, what is it? The most natural choice, which will be the square of the wave function. So you will have a trivial partition function here. By the normalization, it is 1. But this doesn't matter. What your condition is, you can consider the following condition that is, for example, you are given some Hamiltonian here. It is in terms of x and p. So here I'm taking the inner, so expectation of OH and HO. Suppose I'm looking at some eigenstate of the Hamiltonian. What will I will get? It is some constant E. And this is a Schwinger-Dyson equation. You can think of it that. And you will also have the word identity if you have the symmetry and the positivity. Here the positivity is obvious. It's just the positivity of the Hilbert space. Yeah, so you suppose you are given a Hamiltonian, say what it is. Let's say it's a harmonic oscillator. That is H equals T squared plus X squared plus, yeah. This model is also exactly solved by some resurgence theory. And what you will get, well, is using the bootstrap, you can change different E expectations, eigenvalues of the Hamiltonian, and you will get several islands for each eigenvalue because it has a discrete spectrum. When you are increasing the bootstrap cutoff, you are taking into account more and more operators. This island of the E, different eigenstate, it will be shrinking. This is how it works. Okay, so this finishes our discussion of the preliminaries. We go to our.
I have a question. In these two examples, I believe that the series is Borel summable. Is this
Sorry?
The series is Borel summable in both. So is there a reason why you choose them to be Borel summable? Is there a connection between bootstrapping them and this fact?
Yeah, this is a nice point. It seems I can just draw some vague observation. That is the complexity of the Schwinger licensing system. It is closely related with solvability of the real system. So this system, if it is Gaussian, it is trivial. So just by the Schwinger-Dyson equation, you can solve everything. So you add a factor, it becomes less solvable, but still solvable. You will find all the higher quantities, higher moments, they are expressible in terms of W2. So if it is a two-dimensional system, let's say x and y with some exponential potential, then you will get, let's say, maybe several. So you look at the higher moment, it is expressible in a finite amount of lower moments. When you have more dimensions, this number is growing. So if you consider some real problem, let's say the lattice system we are going to consider, that is lattice-Yamil system. If you are introducing one more equation, sometimes you are introducing 7 more variables. So there are much more variables than the equations. So the only solution here is the positivity. You introduce new variables, but you get more you introduce more equations, you get more variables, but you have more inequalities to consider. And the final result is converge. That's the observation.
If you change the sign of the quadratic term in both of these examples, will everything work?
Quadratic term.
Yeah, so for example, in your zero-dimensional action, the quadratic term 1/2, you put the minus sign.
Yes,
but
it works.
It works.
Yeah.
So that's not
So
borrowed.
so there is no problem then. Just
Yeah. This one I didn't show it explicitly, but for the matrix model I tested it already. Yeah, here is fairly non-trivial things will happen. Because for the larger matrix model, it has infinite degree of freedom. Okay, so the bootstrap, this is a picture. And our topic today is lattice gauge theory. That is the conventional Wilson action on the square lattice in 2D, 3D, and 4D in the larger niche. So the question is, what do we want from this model? That is, well, if you say you want a Nobel Prize from this model, this is too ambitious here. So here, the main thing we want to consider is the Wilson loop theory. So the Wilson loop in the larger niche, its expectation contains all the information of the theory in principle. So this is a comparison between our toy model and the lattice-Yang theory. So the observable WK here becomes a Wilson loop, some Wilson loop average on the lattice space, 2D, 3D, and 4D. And the action from the particle action to the Wilson action, these are trivial. And the equation of motion, the corresponding one is the Marquardt equation. And the symmetry here, there is a Z2 symmetry, but it becomes on the lattice, you have lattice symmetry plus chart conjugation. And the positivity, here is a Hankel matrix, but here we have multiple kind of positivity matrix. I will show it here. And the toy model, it is convex, but you will see that the lattice Yang in the larger millimit, it is not convex. Yes?
Don't you also have central symmetry?
Sorry?
Don't you also have a one-port symmetry or central symmetry?
In this work, we didn't take it into account. Yeah, it is possible to
It seems totally vital for those schools.
Sorry?
It seems completely vital for those schools.
It's work around the space.
But for calculating them,
Yeah.
yes,
I mean, I think they use loop equations. It must be built in there.
of course.
Yes.
Yeah.
I did take it into of course.
Yeah, we can discuss it later. That's a very interesting problem.
Maybe you can make it more.
Yeah, sure.
But then
Okay, so McDonald equation, it is just the same story. You are making some shift on some variables and maintain its unitarity. This picture looks very confusing, so I will show you with some simpler example. That is the 2D lattice. What will be the loop equation looks like? Well, the simplest one, you are doing a small shift on some lattice here, and you get the following equation. This equation, it is bounded by the length. The length of the Wilson loop is 8 here. Lambda is a top coupling. And this is another example that is less trivial. You're doing a shift on a backtrack. This backtrack to unitarity is equivalent to the original one bracket. But when you are doing the shift, there is something interesting or something non-trivial. Here is you got the backtrack loop equation that's independent of the host coupling. That is, whatever the host coupling is, in the strong coupling or weak coupling, you always have the inequality. And for the positivity, you have the permission conjugation. So you take the permission of the path, you get the reverse of it. So you take the positivity matrix on the diagonal, you got 1, but off diagonal, you got UP, the one bracket. Here the result is trivial. This determinant, it is positive. So UP, the absolute value smaller than 1. This is something like a trivial argument. But if you consider more and more different starting point and end point, if you consider more paths from 0 to x, then you may get less trivial result. For example, this is one of the lowest order example, that is, you are consider different possible configurations from 0 and then F0. So they are all different Wilson paths in different direction or different space-time rotation. So in the diagonal, you got always one, but off diagonally you get some non-trivial Wilson loop. Of course, their length is bound by 8. You are just solving them. So we can wrap things up. In this matrix, which is a 9 times 9 matrix, you will have 6 Wilson loops, and they are further subjected to 2 loop equations. They are all linear. This is a convex problem. So we can set, let's say, lambda equals 1, and you will get a non-trivial upper bound here. So this is the lowest order. So the lower bound is still trivial here. Well, but this is not the end of the story. If you are consider higher cutoff, it can become super complicated, and it's the whole challenging is a very, very challenging coding. So what is the problem? In fact, the problem is, first, the loop equation is nonlinear. You will have quadratic term. So our answer here is relaxation. We do some relaxation to get rid of this non-convexity here, or non-linearity. And there are more positivity conditions. That is, we usually want more constraints. So here we consider selection positivity. And the positivity matrix, it can become very big. So the answer is symmetry group reduction and some selection rules.
But
So
you're
yeah.
at the end, how you need to take thermodynamic limit or what?
Sorry?
At the end, you need to take some thermodynamic limit?
What do we? Well, all these conditions are true for large enough lattice. As long as your lattice is larger than the bootstrap cutoff, they are always true.
Does that condition come in because you ignore winding loops?
Winding loops? No, we consider all the winding loops.
But then, why does it matter?
Sorry?
Does the size of the lattice enter anywhere?
Yeah. Well, when you are increasing your bootstrap cutoff, your result is always only true for large enough lattice. So is this clear?
No. Why is it only true for large enough? What is the cutoff? I guess it's the size of the loops, right? The cutoff is
the size of the loops.
So you truncate to particular size loops. So
Yes. Then, well, if you are a small lattice, how should I say?
let's say 10
if
by
you
10.
are small, very small lattice, you don't have this kind of Wilson loops. Their loop equation will get changed, right?
Okay. So,
Yeah.
but in principle, your loop equations are valid for infinite lattices.
Yes.
Right?
Yes.
And if you didn't truncate, you would just solve.
All these
thermo-
conditions are true for infinite lattice.
You would solve the thermodynamic problem directly.
Yeah, this is the benefit of bootstrap.
Oh, but then you have infinitely many variables and infinitely many equations.
So he
Yes.
says truncating to Wilson loops of particular size. So he has no information about Wilson loops of large size.
But isn't that exactly what you want though? Don't you want to understand Wilson loops that are big compared to the lattice cutoff?
Well, then you need to push to very, very big cut.
But is there a hope for that?
Ideally, yes.
I will discuss it later. Yeah, but we are running out of
Like,
time.
how do you choose the lattice action? You can add plaquette, or it could be something more complex.
Yeah, I mean the improved action, right? The improved action that is higher other than Wilson action. Is this what you mean?
How do you know which one?
No, they use loop equation for the Wilson action.
Why?
Well, you
This
must
is
make
what
the
they're.
choice.
This is gives them recursion relations of Wilson loops, and okay, it's just they start with that. So it's a particular action, bootstrap.
Okay,
Are
sure.
you asking how to go to the continuum?
Yes, I will
One
discuss
can
later.
you probably give the same answer. So maybe you have
That's
to
right.
choose something very convenient for the lattice.
That's right. It would probably make more sense to impose some universal loop, continuum loop equation.
Yes. So this is, I will pick one point to do a brief explanation because it's already running out of time. This is the positivity in the 2D, right? And it is equivalent to the following equations, just just due to the group theoretical reason. That is, each positivity they correspond to some irreducible representations of the symmetry group. So we have already seen the positivity they are organized by the irreducible representations of the symmetry group, right? For example, the S matrix. You demand the positivity of the S matrix, then you find the unitarity for each spin channel. Okay, this is the final scheme. I won't get into it. And this is a 2D. This is a 2D result for different cohort coupling. And let's look at the 4D result. So this is, you keep increasing the bootstrap cutoff. This is 8, 12, 16, and this is upper bound, lower bound. So in the middle here, this is a non-color result for SU10 and SU12. And the dashed line, they are the weak coupling perturbation. So for very small lambda, actually the Monte Carlo result, the bootstrap result is better than the Monte Carlo, because Monte Carlo you suffer from the finite lattice and the finite n. You are not really doing large.
Sorry, what's on the y-axis?
Access.
It's a plaquette, actually.
Oh.
Yeah. This is a plaquette. In principle, you can bootstrap anything under the bootstrap cutoff. Under some cutoff, you can bootstrap everything. Taking
By
the
Van
upper.
Wilson.
So, can you again say what are the various curves?
Sorry?
Can you again say what are the various curves?
Yes. This is L max equals 8. We have already witnessed that in 2D. That is, you will have a upper bound, but you don't have a non-trivial lower bound. And the orange lines, they are the upper bound and lower bound for L max equals 12. And the blue lines, they are the L max equals 16. Our general experience tells us that this is an exponential convergence. But the cost of computation you are pushing to the higher bootstrap cutoff is also exponential. So it's not so easy.
And then the dots are.
The dots are the Monte Carlo.
Monte Carlo.
Yeah.
And one of them seems to be tracking the upper bound very closely.
Yeah, see, there is some reasons. What is the reason? The reason is that the Wilson action, your action, what is the action? Your action is minus of plaquette. This is a Wilson action. So you want to minimize the action. So you want to maximize plaquette. So that's why in the weak coupling, it is so close to the upper bound. But why this argument fails in the strong coupling? Because the Wilson action is suppressed 1 over lambda by the host coupling. In the strong coupling, it is some other entropy dominant.
But you have multiple dots here.
Yeah, they are from different sources of Monte Carlo.
But they
So-
should overlap if they have the same action.
Yeah, but they are not, because this is SU10 and this is SU12. This is from Kepler and this is from Anderson and Kuczynski.
Oh, sorry, but there's a dotted line as well.
Dotted line is perturbation. Three loop.
Oh,
This
okay.
is 3 loop weak coupling perturbation, and this is a strong coupling.
Okay. Dotted line is not Monte Carlo.
Yeah, not one.
And in this diagram, the continuum limit is like lambda going to 0. That's where the correlation ends.
Yes, this is a limit that you want to take it to the continuum.
It's not an interesting result because perturbatively you can measure a single plaquette Wilson. The interesting result is large Wilson. So they're just showing that in principle this works. Perturbatively you can get it. Perturbation theory is perfectly fine.
Yeah.
There's a principle.
Mhm.
Have you tried to push it to large Wilson?
Yes. Pushing there is some technical difficulty.
You don't sound too enthusiastic.
Yes, L max equals 24, it seems very hard. This is very hard. I can easily create some optimization problem that takes several terabytes of memory. Yeah.
Sorry, that's the cutoff for Bootstrap, but I guess you were asking about the size of the Wilson loop, which was a single plaquette.
Yeah, it's the same thing. We are cutting by the size of the Wilson loop.
So we misunderstand, but you're calculating it for a single Wilson.
Yeah, under this bootstrap, you can bootstrap everything. Under this cutoff, here we are bootstrapping, taking the maximum and minimum of the Wilson, the one plaquette, right? Then you can also take some other different Wilson. That's the thing.
10 by 10 plaquette.
Yeah, 10 by 10, that's already 40. That's too much.
So do you have expressions for the string tension from the previous?
Can you see area law?
Not yet. Not yet. This is well, the area law. If you can get some evidence for it. This is a very conservative argument. Yes. So among this this exploration, the last two is seems pretty promising. The first one is in continuum, that is, if this works, it solves a lot of things. And the last one is not large but finite. I can show some initial results as a conclusion. So this is, let's say, this is a Ikuji-Kawai model. So this is a matrix model. This is U2 and U2, and also you can do some SU3, and you can compare it with U infinity at the same cutoff. You see that finite n is essentially much easier, or it converges much better than larger, due to some not very clear reason, especially as you do, it converges very fast. Yeah. Okay, let's continue.
Any quick questions?
Yeah.
Was this last thing twisted Iguchi-Kawai or what was
Yeah, it is Ikuji-Kawai. Oh no, not even Ikuji-Kawai. I can explain you. I can write it.
So it's just a
Yeah, just
to a single plaquette or what?
yes. In the 2 dimension, it is equivalent to the Yang-Mills.
Yeah, but above it would be.
Yeah.
Good. So it's not twisted Iguchi-Kawai.
Yeah, not even
My
Ikuji-Kawai.
question is, can you apply your techniques to twisted Iguchi-Kawai, which at large n should be the same as the infinite volume Yang-Mills, but with one plaquette?
Well, it seems for the Ikuji-Kawai, if you really write the loop equation, they are pretty similar to the lattice. So if we want to do it, why don't we do it on the lattice?
Well, yeah, twisted Iguchi-Kawai is on the lattice.
Yeah. So it is the same thing. We prefer to do it on the lattice because on the lattice we have the reflection positivity. But in the twisted Ikuji-Kawai, you don't see it. That's a bit mysterious. Yeah, because on the lattice you have some space, right?
So is the kind of the hope of this approach that you might eventually be able to do things which are not accessible to Monte Carlo?
Well,
What is this?
I would prefer the continuum approach because you see the bootstrap, it relies on the symmetry a lot. So bootstrap is basically our techniques to take advantage of the symmetry of the system. So by taking the lattice as a UV regulation, you break some symmetry. So we don't want it. We want symmetry preserving UV regulation. That's the whole idea.
But wouldn't you hope that some sign problem, like problems could be, for example, I'm giving quantum mechanics particle on a circle with a theta term. Could you bootstrap that? You could add a theta term.
I think there is a study of that quantum mechanics with theta term. I will check it. We can discuss later in person. I'm not sure what is their conclusion.
Because you seem to be able to measure some small plaquette things, and you could try to test the theta equal pi whether T is broken, which it should be for Yang-Mills theory, even with local expectation value. That is completely inaccessible.
Didn't you say the sign problem kills it?
No, he said it in this zero-dimensional quantum mechanics, but there's no, there's no T symmetry, there's no reflection positivity in this. This is not a physical problem. Whereas here, there's a Hamiltonian which is positive for theta equal pi. If you just put a generic phase, maybe it doesn't work. But then, you don't have a Hamiltonian for a generic phase. But for some physical problem, maybe there's some positivity conditions which will work.
Okay, if you have any questions, you can ask me later in person.
Thank you.